The medical device industry has its roots in foundation materials such as glass, rubber, metal operating room equipment. However, over the past decades, with the development of polymers and plastics, things have started to change. For example, we have polyvinyl chloride. Polyvinyl chloride. It's just made from vinyl chloride. This is a vinyl group. When you see this C double bond C with H, that's a vinyl group. So that's what forms polyvinyl chloride. And it's used extensively for IV bag production. And this is an example of one of the processing plants where you have the bag material coming off the spools, and it's going to get processed from different rolls to other rolls, and eventually it's going to get cut, it's going to get holes punctured into it, it's going to get graduations for you to know the volume, and in some aspects even filled through a processing line. Another polymer is silicone. In this particular case, we have methyl CH3 from methane. Methane is CH4. If you remove one H, that's methyl. So we have methyl CH3, CH3. We have two. Instead of saying two, you can say di, Di. 2 equals Di in organic chemistry. So we have poly, because we have this N, polydimethyl siloxane, this SiO-Si bond, siloxane. And silicone, here you see it coming out white hot and being formed into a tube after it's extruded through a die. And in this particular case, you could even see the hole in the center, right? So that's how the die allows it to be processed, where you have this kind of tubular shape where there's hollowness on the inside. And you feed your silicone material in to an extruder, and it goes through a die and comes out in the desired shape. And here it's being processed with temperature as well. Sometimes there are monitoring systems, in this particular case laser monitoring systems, to make sure that you are on target with your specifications. And then there might be residual materials where you have to cool down the silicone to get the residual materials to be extracted from the polymer that you just made. So you see in this particular case it's just being cut, and you see how it's being processed, and it's used for tubing, as mentioned, a lot. So these are some of the things that displaced the old methods of doing things in the medical device space. Another one we can think of is the polyolefins. It kind of sounds complicated, but it really is not. You just have a polymer that is produced from a simple olefin, also called an alkene, and it has this alkene group here, right? You have this double bond on this straight chained alkene. So for example, polyethylene is the polyolefin produced by polymerizing the olefin ethylene. In this particular case, what I'm showing you here is 1, 2, 3, 4, 5, 6. What is that? Hexene. So you might be able to create a polyolefin from this. So practically, polyolefins for practical or commercial importance are polyalpha olefins. So here, that's where we have this alpha. And it's a polymer made by polymerizing the alpha olefin. An alpha olefin is an alkene where the carbon-carbon double bond, as we see here, starts at the alpha carbon. That is, it's between carbon number 1 and carbon number 2. So here's an example. Here's an example of a polyolefin, in this particular case polypropylene, being used as a tray, right? A kidney tray for medical devices. So Sometimes it's this simple or this simple looking. And also, we've had fluoropolymers for IV catheters. When I hear fluoropolymers, I immediately think of Teflon because polytetrafluoroethylene. You have 4 fluorine atoms on this particular monomer that forms the polymer for PTFE. And then we have PVDF, PCTFE, etc. So those are some that you can look up. PVDF, can you imagine what that is? What does this look like? Well, we have C, we have HH, we have C, we have FF, we have poly. So anytime you have C double bonded to C and H2, that will be a vinylidene group. So this C and this CH, vinylidene group. So this is polyvinylidene difluoride. So 2 fluorine atoms, difluoride. Polyvinylidene difluoride. And if we break it out so you can see the chain, C difluoride, vinylidene here, difluoride, vinylidene. That's just expanded it. Now, what is this? Whoa. Well, we have PCTFE here. So, polychloro trifluoroethylene. Polychloro trifluoroethylene. Polychloro trifluoroethylene. These are some of your fluoropolymers, but they can get more complex, right? This is an example of a fluoropolymer as well. They don't all have to be as simple as what we're showing. Let's take a look at catheters just as a reminder of what a catheter is, and we'll look at one from Braun.
The B. Braun Intracan Safety IV Catheter with Passive Safety Technology. Safe and easy to use, resulting in first stick success. B. Braun's proprietary universal bevel on the Intracan Safety IV Catheter is a super sharp needle that provides flexibility of insertion angles. The universal bevel creates a V-shaped tricuspid incision, resulting in a flexible pathway for easy and smooth catheter insertion. The result is less tearing and faster healing, greater comfort for clinicians and patients. Intracan Safety's double flashback technology improves first stick success through quick visualization of both the needle flash and the catheter flash. Here's how the double flashback technology delivers this benefit. Upon insertion, the first flashback of blood, needle flash, is visible in the clear flashback chamber, confirming the needle tip is in the vein. Using the push-off plate on the catheter hub, the catheter is advanced forward off the needle into the vein. A second flashback, catheter flash, occurs between the catheter and the needle, confirming that the catheter is successfully in the vein. Once the catheter is advanced completely, the needle is withdrawn in a swift continuous motion. The safety shield on the B. Braun Intracan Safety IV catheter engages as the needle tip passes through the catheter hub. It deploys automatically and permanently shields the needle tip. This safety feature cannot be bypassed and is designed to protect against needle stick injuries. The removable vented flash plug provides additional versatility to the Intercan Safety IV catheter. The flash plug can be replaced with a syringe or blood collection access device prior to insertion, or loosened to speed blood return during catheter insertion. After needle removal, this feature allows the clinician to obtain a droplet of blood for procedures such as monitoring glucose or hemoglobin levels. The B. Braun Intercan Safety IV catheter. Safe and easy to use, resulting in first stick success.
So Teflon is huge, and some of you may have heard of it or even used it in applications before. And the funny thing is, it was discovered by mistake. Isn't that something? So sometimes you just work hard and you discover something by mistake. Now, as you saw the example of the catheter, you can imagine, why would someone want to use something that's a fluoropolymer? I think you already have some sort of idea, because when you're using your pans, they're non-stick pans, right? So they have non-stick and friction reducing properties. The medical device industry is growing. It's currently estimated to be 475 billion here in 2020, and it's estimated to reach about 600 billion in 2024. So as you see these advances, there are many more taking place impacting the industry.